Okay, now that we have gone through an example using the graphical method, let's look at the linear programming model in a more formal way and also discuss some important prerequisites and concepts and so on. So the model that we solved of how many units of base and how many units of XP models to produce so that our net profit will be maximized within the constraints, so that can be expressed in an algebraic way in this fashion. So here is a linear function that represents profit. $80 a unit for X sub 1, $129 for X sub 2, so that's maximize the profit and subject to a set of constraints. So this is our assembly hours constraint, this is testing labor hours constraint, and these are the two maximum sales constraints. And then we have the non-negativity constraint, because these quantities cannot be negative, X sub 1 and X sub 2. So these are the elements of a linear programming model. So let's look at each of those elements. So first is the decision variable, the X sub 1 and X sub 2. Those are the two decision variables in the example we saw. And there can be any number of decision variables, 1,000, 10,000. These are in large industrial sized problems. There could be 10,000, 20,000 variables. Now the variables, the decision variables, are the variables whose values we want to determine. How many units of base model to produce, how many units of XP models to produce, and so on. So these are called decision variables. This is the first element of linear programming modeling. And then we have the objective function. Now the objective function is made up of these decision variables. So you multiply each decision variable with a coefficient and add them up. So that gives you a linear function. So this has to be a linear function of the decision variables. And this objective function will represent something desirable like profit and revenue, that kind of stuff. Or it could represent something that needs to be avoided, like cost and things like that. So when it represents a desirable quantity like profit, then we need to maximize the value of that function. In other words, we want to determine values for the decision variables that will maximize the value of the objective function. In the other case, we want to determine the values for the decision variables such that the value of the function is minimized. So minimized or maximized. And we use a common terminology for that, which is called optimize. Optimize is the best possible value, whichever way, maximum or minimum. And the third component or element of linear programming is the constraint. So the objective function has to remain, or the value of the decision variables have to remain within the allowed constraints, and these constraints are also made up of the decision variables as a linear function. So multiply each decision variable with a coefficient and add them up, and there are three ways these constraints can be set up. A less than or equal to type constraint, which will represent a resource that is limited, or it could be a greater than or equal to constraint, which would be like a minimum requirement that we have to meet. Like for example, if we have a minimum amount of demand for the two products that in the example that we discussed, then we have to produce at least that amount. So minimum amount of say 50 or 60 or 100 or whatever it may be. Or it could be an equal to constraint also. Suppose if we have a flow type of constraint into a warehouse, X amount comes in and the X amount has to go out of the warehouse, so you have incoming quantity equal to outgoing quantity. So there could be an equal to constraint as well. So these are the elements of linear programming model. Now let's look at some requirements. Requirements for linear programming model. First requirement is proportionality. Proportionality of variables is that if you double the value of the variable, then the double will be the requirement of that variable in terms of resources, like XP model and base model. Base model requires 5 hours of labor for each unit, right? So if you produce 1 unit, you need 5 hours. If you produce 10 units, then you need 50 hours. 5 times 10. So that is proportionality. the variable requirements are proportional to the quantity. Now, additivity is when you have resources needed by several decision variables. They all can be added together. Like base model requires 5 times x1 assembly hours, XP model requires 6 times except 2 assembly hours. Then we can add the two, and that will be the total requirement. So that is the additivity of resources. The divisibility of variables is the decision variables can take values on a continuous line. So it is a continuity of the possible values. In other words, you can have non-integer values also for the variables. You cannot just restrict it to be just integer values. It has to be a continuous string of values, continuous stream of values possible. And this can be a problem sometimes, but we will deal with it in case we need only integer values. Then we have to use what is called integer program. The next LP requirement is non-negativity. That is the x sub 1, x sub 2, x sub 3, all the decision variables can take only 0 or positive values, nothing negative. Linear objective function is another requirement. That is the objective function consisting of the decision variables will have one coefficient for each of them and added up. So it's a linear function. There should not be any non-linearity in the objective function. But also in linear programming, there will be only one objective function. There can be multiple decision variables, multiple constraints, but only one objective function which is either maximized or minimized. The value of the objective function is maximized or minimized. And then we have linear constraints. And linear constraints, each constraint must be a linear function, meaning that in each constraint you'll have one or more of the decision variables, and each decision variable is multiplied by a coefficient and added up. So that's it. There shouldn't be any non-linearity in the linear constraints.